In the previous section, we learned about orthogonal bases and how useful they are. So one of the things we learned about is that we can use an orthogonal basis for a subspace to project a vector onto that subspace. So let's recall this because it's going to be really important for this section. Let's let F1, F2, all the way to Fm be an orthogonal basis for a subspace W. Of Rn. Okay, so what we're going to do now is we're going to take a vector in Rn. Then the projection of x onto subspace W is just going to be the sum of the projections of x onto each one of the vectors in the orthogonal basis. This only works if the basis is orthogonal. This formula will not work if we just have any old basis. We need to have an orthogonal basis for this formula to work. Okay? And so using the formula for vector projection, each one of these little projections onto each of the basis vectors look like this. So the projection of x onto F2 is x dot F2 over the norm of F2 squared times vector F2. And we keep doing that for each vector in the orthogonal basis. Here we're just using the formula for vector projection, for orthogonal projection, that we derived early in the course. Let's see, this should be m, not 3. Okay. And so just to draw a picture to remind you what we're dealing with here. So imagine this is subspace W. So our F's, our basis of the F's here, is forming an orthogonal basis for this subspace. We want the projection of some vector x, maybe this is vector x, onto subspace W. Okay, so what that would look like is something like this. This is the orthogonal projection of vector x onto subspace W. Okay? We notice something, looking at this picture though, we notice something that's going to be very crucial to this section. Specifically, if I subtract the projection vector from my original vector x, then my resultant vector is going to be orthogonal to the subspace, right? This vector here is orthogonal to W. For every vector in W, it's going to be orthogonal to that vector. That's going to be a crucial concept for this section. Okay, so you know what? I'm just going to leave it because that's an important observation. Orthogonal to subspace W. Okay, so in this section, we've seen how an orthogonal basis is a really useful basis to have, right? In this section, we are going to learn how we could take a general basis, not necessarily orthogonal, to a subspace and convert it into an orthogonal basis. To do so, we are going to use an algorithm called the Gram-Schmidt orthogonalization algorithm. Okay, so the Gram-Schmidt algorithm, or the Gram-Schmidt orthogonalization algorithm, or just plain Gram-Schmidt, is summarized here. And it looks complicated, but it's a step-by-step process that once you understand it is fairly intuitive. What the Gram-Schmidt algorithm does is it takes any basis of a subspace, and from that we're going to construct an orthogonal basis for the subspace. Okay? We're going to do it sequentially, which means one step at a time. The way we're going to handle this is we're actually going to construct several subspaces that start small and then build up to the subspace we want. Okay, so W1 is going to be a subspace which is equal to the span of only one of the vectors from our original basis. Okay, W2 is a slightly larger subspace because it's the span of two vectors. The first vector, V1, but then we throw in an additional vector, V2 also. That means every vector in W1 is in W2, but W2 is bigger than W1 generally. It's going to have vectors in it that are not in W1. And then we're going to continue that process. We're going to take W2, we're going to add another vector to its spanning set. Okay, so W3 is again a subspace, but it's a little bit bigger than W2. We're going to keep doing this, adding one vector at a time until we get Wm. Wm is the span of all the vectors in our basis, which means Wm is equal to our original subspace W, right? Our goal is going to be to construct an orthogonal basis for each one of these subspaces one at a time, building up until we get to an orthogonal basis for our full subspace. All right. So to do that, so let's start with W1. Okay, we know V1 is a spanning set for this vector, or for this subspace rather. Okay, so we're going to let F1 to Fm, that's going to be our orthogonal basis. So we're going to let F1 be equal to V1. Now, F1 all by itself is an orthogonal basis for W1. It's not hard to find an orthogonal basis for a one-dimensional vector space because you just need the one vector. It doesn't need to be orthogonal to anything else because it's all by itself, right? So it's almost trivially an orthogonal basis for W1, all right? Things get interesting once we go to a basis for W2. Okay, so we're going to keep F1, and then we're going to add to that a second vector F2. Now, we want F2 to be orthogonal to F1. So what we're going to do is we're going to take V2, the new vector in W2, okay, and we are going to subtract the projection of V2 onto W1. Okay, so going back to our picture here, this is like V2, and we're taking V2 and we're subtracting the projection of V2 onto W1. Okay, that's going to give us a vector that is orthogonal to W1. This vector, F2, is orthogonal to W1, and therefore it's orthogonal to every vector in W1, including F1. So this is going to give me two vectors, F1 and F2, that are orthogonal to each other, and by construction, they still reach the whole space of W2. Okay? And I kind of keep doing this process. Then I get F3. Okay, to find F3, I'm going to take V3, which is the new vector in the spanning set for W3, and then I'm going to subtract the projection of V3 onto my previous subspace W2. What I am left with is the portion of V3, the component of V3, that is orthogonal to my old space W2, and therefore it is going to be orthogonal to the basis vectors of W2. So it's going to be orthogonal to both F1 and F2. So F3 is going to be orthogonal to F1 and F2, and we know F2 is orthogonal to F1, so all three of these are now orthogonal to each other, and they form a basis for W3. We keep that process going. We keep the process going until we get to our very last vector in the original basis and find Fm. That's going to be a basis that is an orthogonal basis. All these vectors are orthogonal. An orthogonal basis of the original subspace W. Okay? So hopefully the geometry of the problem makes a bit of sense. The algorithm is fairly straightforward to implement. We are just taking at each step, the first step, we just take the first vector. Each step after that, we take the next vector in the sequence, okay, in the set of vectors that we have, and we subtract the projection of our new vector onto the subspace formed by our old vectors. Okay, so for this one, for example, we would have V2 minus the projection of V2 onto W1. We know the projection of a vector onto a space. We just take the dot product of the vector that we're projecting with each basis vector, each orthogonal basis vector in the original space. So we do want to use the orthogonal basis, so we want to use the F's here. So this is going to be V2 minus. Now in this case, V1 is spanned by only one vector. Its basis is, it's a one-dimensional vector space, so it just has one vector in its orthogonal basis. So V2 is equal to, F2 is equal to V2 minus F1, V2 dot F1 over the norm of F1 squared times F1. Okay. And then the projection of, and then F3, I'm going to take V3 and subtract the projection of V3 onto W2. So that's going to be V3 minus, and then the projection of V3 onto W2, I just take the projection of V3 onto the basis vectors, the orthogonal basis of W2. The orthogonal basis of W2 is the two orthogonal vectors we found before, F1 and F2. Okay, so this is going to be V3 dot F1 over norm of F1 squared times F1 minus V3 dot F2 over norm of F2 squared times F2. Okay? So notice in each subsequent step, we have to do a little bit more to get there. For the very first step, we don't have to subtract anything. Okay? Finding F2, we need to subtract one projection onto F1. To find V3, we subtract the projection of V3 onto F2 and onto F1. This is the projection onto F1, this is the projection onto F2. Okay? And so generally, making this look a little bit easier on the eyes, we get this. Okay? The first vector in our orthogonal basis is just V1. Second vector, we take V2, we subtract the projection of V2 onto F1. Okay. For F3, we take V3 and we subtract the projection onto of V3 onto F1 and F2, the two vectors, orthogonal vectors we already found. And we keep on doing that. All right. So the algorithm may seem a little intimidating at first, but once you get used to it, it is a fairly straightforward algorithm, and it's a pretty nice way to always find an orthogonal basis for a vector space.